So today we're going to be looking at continuous random variables. Now that phrase, that should sound familiar because we've previously looked at discrete random variables. So we're moving from discrete to continuous, and the variable we're measuring, that's what's going to make the difference. Previously we looked at discrete variables like shoe size, IQ, cars passing the school in a 1 hour period. This would have been the Poisson distribution. We looked at the number of successes when rolling a dice, or the number of successes when taking penalties in a tournament. These would have been the binomial distribution. So all of these variables were discrete, which meant that we had a discrete random variable. We're going to move on and look at variables which are continuous, such as the height of contestants in a high jump, the weight of bodybuilders in the gym, the time taken to complete a puzzle or a task. All of these variables are now continuous, but we want to be able to do similar things we do with the discrete random variables, but with extra consideration for the fact that the data type is now continuous. Let's start by thinking about the visuals. So on the left we have a discrete random variable. The discrete outcomes will go along the x-axis, they're unlabeled, and the probability of each of them happening is going to be the height of each of these bars. We see that there's gaps in between each bars because there are some numerical values that wouldn't count as outcomes. If this was the number of correct guesses you have when attempting 5 multiple choice questions, and the probability of getting 1, 2, 3, 4, or 5 of those answers correct. There is no 1.5 answers correct, so there's a gap in between 1 and 2. On the right hand side we have a continuous random variable, and this could be anything. This could be the time taken to ice skate down a mountain. There are no gaps between one result and the next because time itself is continuous. We don't have 1 minute and 2 minutes. We have to include all the minutes in between. We don't have 1 minute 52 seconds and 1 minute 53 seconds because we have to include all of the potential decimal results in between 52 and 53 seconds. So this is the diagram we'll use for a continuous distribution. So, as I said before, some examples of discrete random variables you've already come across are the Poisson distribution, the binomial distribution, the discrete uniform distribution, and then there's just non-standard discrete random variables. For continuous, we've only up to now mentioned the normal distribution, but we'll look at some other continuous distributions as we make our way through this unit. Some key properties of a discrete random variable. We saw that we knew the probabilities of each of the individual outcomes needed to sum to 1. If we'd accounted for every possible outcome, the probabilities would add up to 1. Implicitly, we knew that probabilities couldn't be negative. They were either 0 or they were a positive value. It wouldn't make sense to have a negative probability. For continuous random variables, in a similar way, the probabilities need to add up to 1. But now, our probability is the total area underneath the graph. And that probability, that area, should sum to 1. We don't have individual probabilities, but we have the function in general. And the function is the tracing of the blue line. We'll soon look at how we can define the function. But our function must always be non-negative, just like the probabilities before. It can equal 0, or it can be positive, but it can never be negative. So we're going to start with the probability density function. The function itself, the height of the graph, the y value, the vertical variable, is not going to be the probability itself. This is similar to when we worked with histograms in straight maths. The height of any particular bar isn't the probability, it's the frequency density. It's a pseudo variable that helped us to calculate frequencies. Here, the function is a pseudo variable that's going to help us to calculate probabilities. In a histogram, we never tried to find the probability of one exact value. The probability that somebody's height was 124 centimeters. That would be one thin line, one thin vertical line on the histogram, and the area of that line itself would be so small that it almost equals nothing. It will be so small, it's negligible. It will be so small, it will be 0.30 zeros and then a 1. So small that we actually don't find it useful to find the probability of one exact value. Similarly, for our continuous random variable, we don't find the probability of exact values. We say that those exact values would have a probability of 0. We find the probabilities of intervals. We're finding the area. We're never finding one particular value, but a range of values, an interval of values, and that is linked to the area underneath the function, the area underneath the curve. And these phrases should start to sound familiar. We can make really good use of calculus, of integration, to find those unknown probabilities. Okay, so back to the probability density function, and let's just formalize some of the points that I've mentioned. So firstly, every valid continuous random variable will have a probability density function where its function is greater than or equal to 0. If you're asked to check whether a probability density function is valid, you should firstly check that this function never goes below 0 for the interval we're interested in. The second property, as I've said, we can use calculus, we can use integration to find the probability in between any two values. And we find that probability by integrating in between those values, by using definite integration of the function. That will find the area under the graph. That area corresponds to a probability. And finally, there's an exhaustive probability. And finally, it's an exhaustive property that if we integrate in between the smallest valid value and the largest valid value, here we've used negative infinity and positive infinity. So if we integrate our function between the smallest and largest valid values for that function, it should equal to 1. And that will help us with some problem solving and finding any unknowns. Okay, let's have a look at an example. Okay, so let's start with an example here. We've been given this function. We're told it's valid in between 2 and 4, and the first thing we're asked to do is to find a value for k. So k is unknown at the moment. If we go back to the criteria of a valid continuous random variable, we know that we should be able to integrate in between the smallest value here and the largest value, and the answer should be 1. This is similar to when we found k for a discrete random variable. We knew the probabilities should add up to 1. So we used that to generate an equation from which we could solve for k. Let's try this out. So I'm going to start by integrating in between 4 and 2, and the function to integrate is kx 4 minus x. Okay, at this point actually, I much prefer to factorize out any constants from the integration, just to make the integration a bit more straightforward. K is a constant, so I'm going to take that outside of the integration. So that's k on the outside, and I'm integrating 4x minus x squared. Okay, so as I transfer this into square brackets and I process the integration, k remains on the outside, and I integrate to get 4 over 2 x squared minus 1/3 x cubed. Limits 4 and 2, and all of this should equal 1. So as usual, so with integration, we're first going to substitute 4 into these square brackets, and from there we're going to subtract 2 substituted into these square brackets. So here's the line of working that I'll show, and it's only at this point that I'll reach for my calculator. I'll process all of this, and I get 16 over 3. So 16 over 3k equals 1. That means k must be 3 over 16. Next, we're actually asked to sketch this function. Before I even try to sketch it, I'm looking at the function and I'm thinking, what type of function do I have? Is it a horizontal line? Is it a linear function? Is it a quadratic, a cubic, Or what type of function do I have? Looking here, I have a quadratic. As with any time you're working with a quadratic, we should really start off by finding the roots. So this function, if I set it equal to 0, I realize that I have two roots, either x equals 0 or x equals 4. With that information, I can start to draw the underlying function. This isn't automatically the continuous random variable. The continuous random variable is going to be this function, but valid over a particular interval. And our interval is 2 to 4. Okay, so let's see what happens. So if I'm sketching this quadratic, here are the roots, 0 and 4. Here's the underlying function. I'm only interested in this function from 2 to 4. So I can ignore the dashed line from 0 to 2. You could keep it a dashed line and make sure the rest of it is solid. So this is nearly a complete diagram. What's missing is that we do have some information about the value of this function when x equals 2. If we hadn't found k, we would want to give this in terms of k, but we have found the value for k, so we can actually give this as a numerical value. Okay, so let's check this out. When x equals 2, what does the function equal? So we'll just substitute 2 into the function. That will give us 3 over 16 multiplied by 2 multiplied by 4 minus 2. So that's 3 over 16 times 4, and in our heads we get 3/4. So when x equals 2, the value of this function is 3/4. And now this would be the complete sketch we were looking for. So we use the criteria that the continuous random variable has an area of 1. So integrating in between its upper limit and its lower limit gave us an answer of 1. From there we found k, and from k we were able to complete our diagram. Drawing the diagram, we had to consider what the function looks like, and then we use that to draw the segment of the function for the interval we're working with. Okay, let's have a look at another example. This time round, there are two intervals and two functions for those different intervals. How do we sketch the function, and how can we use the sketch itself to find the value of k? Okay, so I'm just going to start by getting the axes. I know the values I should be working with from 1 all the way through to 4. I'm going to start with the first function, which is just a value of k in between 1 and 2. So I can label the axes. I definitely have k. Am I going to have 2k, 3k, 4k? So for the value of 1, the function leads to an answer of k. For the value of 2, it also leads to an answer of k. Looking at the function itself, it is going to be a horizontal line of height k. So that's in between 1 and 2. Let's have a look at what kind of function we have in between 2 and 4. Well, this is kx minus k if I was to expand it. And that's a linear function with a positive gradient. So I know I'm looking for a straight diagonal line. As long as I evaluate 2 points, I should be able to sketch the line. So when x equals 2, the function is going to equal k. So that means it connects to what I've drawn so far on the diagram. When x equals 4, it's going to equal 3k. So I know it's going to go through those 2 points. I should just be able to connect them. I could evaluate for 3, and that's going to give us 2k, which just matches what I've done anyway. So here is the PDF. This is the PDF of this continuous random variable. This sketch is valid. We didn't know what k was, so I just sketched in terms of k. Subsequently, we've been asked to find the value of k. So we're going to use that criteria that we know, which is the area must equal 1. The area I can actually find since we have two simple geometric shapes, and I have enough information about their dimensions to get expressions for each of those areas. I have a rectangle, a small rectangle. Its width is 1 and its height is k. I have a trapezium. On the trapezium, the parallel sides have length k and 3k, and the height, which is horizontal, or the distance between those parallel lengths, is 2. So here's an expression and an equation that I'm able to set up. Simplifying, we get 5k equals 1. Straight away from there we can see that k equals 1 over 5. Okay, at this point I could go back and fix the diagram and make that 1/5, 2/5, 3/5 and 4/5. It wouldn't be necessary in this question since we were led to find k after we'd already produced the diagram. So, although the area equaled 1, you can see that here I relied on some GCSE knowledge of these geometric shapes, the rectangle and trapezium. You could have split this into a rectangle and a triangle, but I didn't jump straight to integration. I had a look at my diagram and I thought about the most efficient way to calculate the area. You could have integrated this horizontal line, but that would be a lot of integration to get an answer of k. You could have integrated this trapezium, the diagonal line. That would have been a lot of work to get an answer of 4k. So just being efficient with the technique that you choose to use.